This is Hunter's second attempt at, my second attempt at a reassessment for Newton's second law. Alright, we start off, and what we're going to do here is, you got a bunch of roofers, and they're pulling up some packets of roofing shingles up a roof at a 38 degree angle pitch, or 38 degree angle. And they're pulling it up with a rope up the roof, and the coefficient of friction is 0.5. The mass is 120. The velocity that they're pulling is at 1.5 meters per second, and they're doing it for 2 seconds. And the velocity, they started from rest, so the initial velocity is 0. We want to find the tension on the rope while it's pulling up, and find the acceleration while it's pulling up, because we're not doing a constant velocity. Okay, so what we did here is drew a diagram, and I got the force of tension being pulled up the roof, and the force of friction is pulling against it. Force normal up pushing against the roof, mg pulling down. We set up our mg cosine is the opposite of our normal force. Mg sine is our downward acceleration. So what we did is we said F net is equal to ma. Then we said F net y direction, which is not having any acceleration in the y direction, is Fm minus mg cosine theta equals 0. And then we found out that force normal is equal to mg cosine theta. So then we go ahead and do our force of friction, which is normal times mu. Force of friction is mg cosine theta times mu. Then we're going to go ahead and plug in our numbers, and force of friction becomes 463.3 newtons. So then we're going to go ahead over back to the x side, and we're going to go ahead and do the forces in the x direction, which is force net in the x direction is equal to mass times acceleration. And we say force of tension minus the force of friction minus mg sine of theta is equal to mass times acceleration. So then we're going to go ahead and solve for, we're going to move them over to the other side. Force of tension is equal to force of friction plus mg sine theta plus mass times acceleration. Force of tension, we're going to add them all up, and it comes out to be 1,277 newtons. Okay, now the rope is only able to hold 1,250 newtons, so it breaks and it's sliding back down the roof. So we know there's no acceleration in the y direction, so we're just going to go ahead and worry about the x direction. Now the frictional force is going to change direction. So then what we're going to do in this part of problem, part B, we're going to find the acceleration sliding down the roof. So we're going to say F net x is equal to ma. And then we're going to go ahead and say that for mg sine of theta minus force of friction is equal to the mass times the acceleration. We divide out the masses. Then that leaves g sine of theta minus frictional force over mass is equal to acceleration in the x direction. We plug in our numbers, and we get 2.17 meters per second squared. 2.17 meters per second squared. So then we went ahead and decided to do, if it slides down the roof for 4 seconds, will it fall off of a 4-meter roof? So we got our acceleration is equal to change in velocity over change in time. So then we're going to flip that over. We're going to say acceleration times change in time is equal to the change in velocity. So then we know that the initial velocity was 0, the initial time was 0. So then we can go ahead and plug those numbers in. It gives us a velocity of 8.68 meters per second. Then we know that change in r over the change in time is equal to velocity. So we're going to say that change in r is equal to velocity times the change in t in time. Then we're going to go ahead and say that our final is going to be velocity times change in t times time final. Plug in our numbers. It says in that amount of time it would go about 34 meters. So yes, it would slide off the roof. Alright, thank you for taking time to look at this.